Unit 7, Periodic Properties, pages 146 to 148, focusing on electron configuration of ions. Electron configuration of ions. To find the electron configurations of cations, you remove the outermost highest energy electrons. So here is sodium that is neutral, and it has the electron configuration 1s2, 2s2, 2p6, 3s1. When it has a positive charge, it's going to lose one electron. So we lose it from the highest energy level, which is 3s, and so we're going to lose that one. And so you get 1s2, 2s2, 2p6. You might also see it written as 3s0 to show that the electron was removed from the 3s subshell. Notice that we end up with a noble gas configuration, meaning sodium plus 1 has the same configuration as neon, identical, and so there's a name for that. That's called isoelectronic. It means two different elements with the same electron configuration. Sodium plus 1 is isoelectronic with neon. So if we look at aluminum, neutral here, it has 1s2, 2s2, 2p6, 3s2, 3p1. We're going to lose 3 electrons, so we're going to lose them here. 1, 2, 3. When we lose these 3 electrons, we end up with this configuration, which is isoelectronic with neon, again a noble gas. To find the electron configuration of anions, add an electron into the next highest available orbital. So here's oxygen, and its configuration is 1s2, 2s2, 2p4. And then when it becomes a -2, we're going to gain or add 2 more electrons. So you're going to go ahead and fill up the rest of the p sublevel because it can hold 2 more electrons, making it go from 4 to 6. And then again, you'll notice that we are now isoelectronic with a noble gas, neon. Remember, the goal of gaining or losing electrons is in order to achieve a noble gas configuration or a complete octet. Certain ions take on a specific charge when they make ionic molecules. They do this to achieve a full shell or noble gas electron configuration. This is the reason why oxygen is always O2 negative and sodium is always Na plus when they form ionic molecules. So electron configuration of transition metal ions. So a review of the main group ions. With main group elements, the ion electron configurations seem reasonable. Cation configurations are made just by removing the outermost electrons, and anion configurations are made by adding additional electrons. However, the transition metal ions start to fill the d orbital. The highest energy electron that is removed is from the last filled s orbital. The d orbital electrons are removed last. So when you have iron, here is the configuration of iron, argon 4s2, 3d6. 4s is a higher energy level than 3d. So as I remove electrons, like removing 1 for example, I start removing it from the 4s. So Fe plus 1 will be 4s1, 3d6. And then if I remove a second electron, I'm going to go ahead and remove the second s electron, giving me 4s0, 3d6 for Fe plus 2. And then if you remove one more electron, now that I've taken all the s electrons, I can start taking it from the d sublevel. So these electron configurations may seem unexpected. The reason has to do with the very close energies of the s and d orbitals. The electron configuration of manganese and Fe plus is not the same. Although they both have the same number of electrons, Fe has 1 more proton. This makes enough difference in the energies of the orbitals to make the lowest energy electron configuration of Fe plus 4s1, 3d6, and the electron configuration of manganese 4s2, 3d5. Here's your note card for this section. Cations are going to lose electrons, and you're going to remove them from the highest energy level first. Anions are going to gain electrons, so you're going to add electrons to the next available orbital. Isoelectronic means 2 atoms with identical electron configurations. Most atoms gain or lose to be isoelectronic with a noble gas. Losing electrons in a transition metal. So if you have, for example, 5s2, 4d7, we want to lose from the 5s orbital first, and then once I've taken those 2 electrons, then you start removing them from the 4d sublevel.